So in this video, we're going to look at problem 2.8 from the homework. We're told that the magnitude of F2 is 6.5 kilonewtons. We can see its geometry along a coordinate system that's kind of defined by two axes denoted as U and V. Note particularly that these two axes aren't perpendicular to one another as we're traditionally used to seeing in the majority of the problems that we're going to work in this text. Instead, they're kind of separated by the 75-degree angle that we have depicted in the actual figure. And what we're asked to do is to try to find the components of that vector F2 along the U and V axes. And I picked to include this problem in the homework because if you remember when we did the Chapter 2 lecture, I mentioned that although we weren't going to cover a lot of the geometrical techniques for actually doing vector addition, that it was something that you should take a look at kind of on your own time. And this is a problem that is actually more easily solved using kind of geometrical techniques, I guess I would call it. It is still the triangle rule of addition, only we're not dealing with right triangles, so it's not going to be a lot of SOHCAHTOA and Pythagorean's theorem. Instead, it's going to be the law of sines. So if you notice, the first thing that I did is I just reconstructed the figure as I was given in the text. And what I want to do is kind of envision how I could draw F2 as the sum of two vectors, one which is a line on the U-axis and one which is a line on the V-axis. And at least to me, it's pretty easy to see what the kind of decomposition of that vector along the U-axis would look like, right? It would go from the origin or the point of intersection of the U and V-axis, and it would extend along the positive U-axis. Now, if I want to follow the tip-to-tail definition of the triangle rule of addition of vectors, you notice that my vector along the V-axis is actually going to point in the negative V direction. It's going to be directed back to the left, and we can kind of sense the sign convention of positive U and V from the tips that they've actually drawn on the U and V axis. In addition, as you might remember, as I discussed in the lecture, if you curl U into V, you would expect that positive U would curl into positive V. So if you know that concept from calculus, that's great. If you don't, just view it as the arrows is representing pointing in the positive direction of each axis. So kind of before I show you the triangle, you notice that F2 is going to decompose into a component along positive U and then a component along positive V. But notice that the component along positive V isn't going to be at a perpendicular angle because the relationship between these two axes, they're not separated by 90 degrees. They're only separated by 75 degrees. So as you can see in the forced triangle that I've drawn, here we have F2 decomposed into a component along the U-axis and a component along the V-axis. Notice that the kind of angular separation between the U and V-axis is 75 degrees. So that is an angle that I was actually given in my description here. So that's just translated down to my triangle. And then in my original triangle, I have F2, and I know its separation from the U-axis is 30 degrees. I know the separation between the U and V-axis is 75 degrees. And in addition, I know that all of the angles inside a triangle must sum to 180 degrees. So I can compute this additional angle in my triangle that kind of represents the intersection of the tip of F2 with the tip of the V component of F2. And that is just going to be 75 degrees. So it just happens to be, it's not that it's equal to this angle, it's just that all three of these have to sum to 75 degrees. So what I have is a situation where I know the three interior angles of my triangle. In addition, I know the side length corresponding to the magnitude of F2. That is one of the things that I was given, 6.5 kilonewtons. So if you remember back to your geometry class, whenever you took it, if you have a scenario where you know all of the interior angles of a triangle, and you know one of the side lengths, you can iteratively determine the other two side lengths by using the law of sines. And the law of sines is nothing more than saying that the ratio of the side length to the sine of the matching angle is consistent for all three side lengths. So since I know F2, the side length, and again, we're kind of calling it a side length of a triangle. Remember that technically we employ a lot of the ideas of triangle geometry when we actually do vector decomposition. So the length of this side length in a triangle actually corresponds to the magnitude of this force, which we were given. So since we know this side length, we will match it to its corresponding angle, which is 75 degrees. Then we'll just pick one of the other two side lengths that we want to solve for, and we can pick either because we have both remaining angles. So if you notice what I did here is I chose to solve for the U component of F2 first. So I said that the ratio of F2 to the sine of its matching angle, which is 75 degrees, must be equal to that unknown component of F2 along the U-axis divided by the sine of its matching angle, which happens to also be 75 degrees. So again, I want to be clear, these two 75s, even though they're the same number, they correspond to different angles inside the triangle. So I can solve that for the u component of f2. It's going to be nice because when I multiply both sides by the sine of 75, it will just go away. And what I will find is that the magnitude of the component of F2 along the u-axis is just 6.5 kilonewtons. So hopefully that makes sense to everyone. And again, as I mentioned earlier, that is pointing in the positive u direction. So I don't need to do any sign adjustments there. In a similar fashion, I'll do the same thing to determine this side length, F2V. I'll take the ratio of F2 corresponding to the sine of its angle, which is 75 degrees, and that will be equal to the ratio of the side length I want to actually find, which is F2V. And remember, in a triangle, the matching angle is opposite of that side length. So that will be in the denominator there, I will add the sine of 30. And if I follow the same procedure, I will be able to solve for F2V in terms of its magnitude. It is 3.4 kilonewtons, that is the length, but remember it is on the minus V axis. So you always have to be careful when you're working and mastering engineering. Sometimes they will want that sign explicitly in there, sometimes they won't. When we actually do exams and whatnot, I'll always go back in, and if I can kind of trace and remember, in that case, you're going to write out your work and scan it as well. And as long as I can tell that you kind of have the correct idea, I will be sure to give you full points for that. But for the homework, do try to always give them what they're asking for. It kind of avoids that intermediate step of me having to go back in and correct.